from VectorOLE.
That's right. Thanks very much for the introduction, Abby, and thank you for inviting me here. So yeah, this talk is mostly based on joint work in a paper with Carsten, Alex, and Mark from Aarhus and Galois. And we're part of the Fromage team for the DARPA Civ project, which you might have seen Josh Barron give a talk about last week. So I'm going to talk about using a primitive called Vector-OLE to build a large scalable zero-knowledge protocols. And the setting we're interested in is the standard two-party zero-knowledge setting. We have a prover and a verifier. And for this talk, I'll just consider the statement to be represented as some arithmetic circuit C over a finite field. So the prover has a witness, which is a vector of field elements. And after the protocol, the verifier accepts if and only if the circuit applied to the witness outputs 0. So it's satisfied. And the goal within this setting is to be able to achieve zero knowledge for very large scale statements. By this, I mean doing proofs about, say, programs with maybe billions and billions of instructions, whilst maintaining a fairly low computational and memory overhead on top of just the resources needed to evaluate the program in the clear. So ideally, we don't want to have the prover or verifier to have to load the entire statement to memory so that they can process this in some kind of streaming manner and output the proof. And the approach we'll be doing to do this is taking some techniques which have been developed in the multi-party computation community over the last couple of years, namely Vector-OLE, and applying this to the zero-knowledge setting. Now, of course, this goal is very ambitious. So we're going to have to make some relaxations towards achieving this. And the places we're going to be losing out on a little bit in this is we're going to have possibly interactive protocols, and also in the designated verifier setting, and not succinctness. So typically the proof size or the amount of communication will scale linearly with the circuit size, although in some cases this can be reduced. Okay, so now a very quick overview of what I want to cover, which is firstly using the Vector-OLE primitive, well, first explaining what it is, and using this to build a simple kind of homomorphic commitment. And then plugging this into our first main protocol, which is a commit and proof type ZK protocol for arithmetic circuits, which we call mac and cheese. And then I'll briefly talk about two variants of mac and cheese, where the first one is aimed at getting something that's non-interactive and suitable for the streaming setting. And the second one is an optimization, which we apply to reduce the proof size, so going below linear in some cases, especially when we're looking at proving disjunctions of statements. Okay, so as I've said, the main tool that I'm going to be using is called Vector Oblivious Linear Evaluation, Vector-OLE or VOLE. This is a two-party primitive, so here just between the prover and verifier, where the ideal functionality of this primitive is represented in the box on the slide here. So the prover inputs on the left some input x, which is a field element, and the prover receives output, this alpha x plus beta, where alpha and beta here are randomly sampled by the functionality and given to the verifier. So in a Vector-OLE, in contrast to a standard OLE, we're particularly interested in the case where we have many iterations or queries to this functionality, where the restriction is that this alpha value given to the prover is going to be the same across every iteration. So think of it as the prover inputting x and receiving back this linear function, alpha x plus beta, where beta is random, but alpha is fixed. And what we can exploit is the fact that in the last few years, some very efficient protocols based for Vector-OLE have been established based on a variance of the learning parity with noise assumption from a series of papers in the MPC community. And these protocols are very efficient. They have very low communication requirements. So to produce a batch of Vector-OLEs on random inputs, so where the x's are all, say, pseudo-random, the amount of communication is essentially independent of the number of instances you want to produce. And the computational footprint is also very low, like order of 100 nanoseconds for a single Vector-OLE output. Okay, so given this building block, what are we going to do with it? Well, for a starting point, it's quite straightforward to see that a Vector-OLE already gives you a form of information theoretic MAC over the finite field. So if we look at a random Vector-OLE where instead of a chosen input x, the prover inputs some random value r, and view the prover's output as a MAC m, so alpha r plus beta is a MAC on r under the MAC key alpha and beta held by the verifier. Well, because this MAC is just a linear relation on the MAC key, this gives us a linearly homomorphic MAC scheme. And it's also sound. It turns out that if the prover wants to come up with a valid MAC on something not equal to R for the same MAC key, then the only way to do this is by guessing the key alpha, which if it's random in the field will happen with negligible probability for a large enough field. Okay, and we'll take this one step further and model these information theoretic MACs as actually a kind of interactive commitment scheme. So we have two protocols, a commitment protocol and an opening protocol. The commitment takes input x from the prover, and I'll use this square bracket notation to denote that x is now committed towards both parties. So to commit to x, you just take a Vector-OLE with input x, which gives you the MAC on x. But we actually write this in terms of taking a random Vector-OLE. So we start with the m equals alpha r plus beta for a random r, but then have the prover send over some correction value. So d is x minus r, which allows the verifier to then update its local MAC key by adding alpha times d to the key beta. So previously we had m is alpha r plus beta. Now with this adjustment, you get a valid MAC on x instead of r. And opening these commitments is simply just having the prover send over the message and the MAC on the message for the verifier to check the linear relation holds. So the nice thing about this is that compared with, say, commitment schemes based on discrete log assumptions or lattices or something, and we have this like optimal commitment size where the prover just sends a single field element to commit to a value, then after that, all the operations, information theoretic, the computational cost is very, very low. And this is what allows us to achieve this goal of being able to scale up to large proof statements without requiring excessive computational resources. Okay, right. So now once we have homomorphic commitments, I'll talk about the mac and cheese protocol. And here I'll just present the kind of simplest variant of the protocol. We have a few other variants in the paper, which are more efficient in some cases. And it's essentially a standard commit and prove type protocol where the prover starts by committing to the witness, W1 to Wn, each as a field element. And then the parties just jointly evaluate the circuit in a gate-by-gate fashion. So since the commitments are homomorphic, at every gate which is an addition or scalar multiplication, you can obtain a commitment to the output of the gate completely locally. So the only challenge, as usual, is going to be multiplication gates. So suppose we have two commitments to x and y, and we want to obtain a commitment to the product x times y. Then the prover will commit to a value z, which is allegedly the product xy. And then to verify this, we'll have the prover commit to some auxiliary value c, which is a times y for some extra random commitment a. Now, the verifier then sends a random challenge, and the prover responds by opening some value e times x minus a. So this is a linear combination of the commitments x and a, which can be computed publicly and then opened by the prover. And this check and challenge response is going to allow the verifier to check the correctness of the multiplication. So again, both parties compute a linear combination of the commitments as e z minus c minus epsilon times y. I won't go into the details of why this works, but it turns out if the multiplication is correct, then this should equal 0. And if it's incorrect, then you'll essentially get something random. And to be able to force this check to pass, the prover would have had to guess the challenge E in advance. So the parties obtain this commitment to something which should be 0 and then run this assert zero procedure, which verifies the contents of the commitment contains zero. And this can be done just by opening the commitment, or also more efficiently by batching things together. Okay, so that's the basic protocol for evaluating circuits using the simplest form of mac and cheese. So now let's look at this in a little more detail. Here's the same multiplication check on this slide. And think about how this works in a streaming setting. So actually, this protocol can already handle streaming as we want it. So there's no state required between multiplications. We can just kind of stream the circuit as we come in and then run this interactive protocol every time we come across a multiplication case. Now, of course, there's kind of a major downside here, in that every time we get a multiplication, we have to add this extra round of interaction. We get a random challenge, and the prover responds back to the verifier. So that's not so nice if you say the parties are over a high latency network, or they don't want to be online at the same time. So possible alternative is to batch these multiplications together, which can allow you to get just a constant round complexity. But unfortunately, this requires you to then store everything in the batch, which you're doing in memory at the same time, and it's no longer constant memory or streamable. So it seems like there's this kind of inherent trade-off between the round complexity and the memory complexity, but actually we can avoid this. What we do is conceptually very simple. It's just to take the low memory, but many rounds protocol, and apply a variant of the Fiat-Shamir transform. This squashes the round complexity because we sample the random challenge E as a hash of the previous messages and the previous transcript. So then in each multiplication, we just have the messages from the prover to verify the opening and the assert zero statement. And we show that we can also do these in a similar kind of a Fiat-Shamir check, so that these can be batched, these can be evaluated with a minimal interaction with no messages from the verifier. Now, one potential issue with this is that because we're applying Fiat-Shamir to a many round protocol, then if we look at like some of the generic bounds on the resulting security of a protocol, you can often get something which degrades very badly in the number of rounds. It turns out in this case, we can show that for these types of protocols, we actually have a kind of round by round soundness property, which shows that the security loss when applying this transform only depends on the number of queries to the hash function and not the round complexity. So we essentially get this Fiat-Shamir for free with this nice streaming property.
So Peter, if you want to maintain the constant memory, how do you hash the previous part of the transcript?
Yeah. So you have to then maintain the previous hash from the last round and include that as input to the hash in the next round. So the hash. So you don't hash the entire transcript. You just hash all the messages since the last round and the previous challenge. Okay. Right. So the second variant of the protocol I talk about is towards optimizing disjunctions in these commit and prove type protocols like mac and cheese. Okay, so a disjunctive statement is can just be seen as several different statements where we want to prove one of these is true. So here we have, say, m different circuits, and the prover knows a valid witness, which corresponds to one of them. We want to prove that one of these is satisfied without revealing which one. So a classic approach to proving a disjunction of statements is to use an OR proof from this paper back in the 90s by Kramer, Damgaard, and Schoenmakers. The problem with this OR proof protocol is that you then get a communication cost in the protocol, which basically corresponds to the sum of all of the different branches in the disjunction which you want to evaluate.
Just a second. Are these branches of the same structure, or are they different circuits?
Potentially different circuits. So it works a little better if you have the same structure, but it's not necessary. Okay. Yeah, so the goal is to communicate only the information proportional to the longest branch in this setting. And the main observation in allowing this is that if we look at, say, the multiplication protocol from the previous couple of slides, then all of the messages which are sent from the prover are actually just random messages. So you can show that the transcript is basically pseudo-random. So it's apart from these special assert zero statements where you're actually verifying some MAC or some commitment. So then the verifier doesn't actually need to know whether this transcript comes from the proof for statement C1 or for statement C2. So as a first attempt, you can say, okay, let's just run the protocol for the true branch as the prover. The verifier is anyway responding only with random challenges, so that doesn't matter. And the verifier can use the same messages to evaluate both possible proofs. But now the challenge here comes in when we actually want to complete the verification of the proof. So in the mac and cheese protocol, this is where we have these assert zero statements, which actually verify the prover was doing the right thing. Now, obviously, we can't run the assert zero statements for all the branches because that would reveal which branch was correct. So we show that we can actually phrase these assert zeros as a kind of miniature OR proof, where we want to check that one out of the m sets of assert zero statements within the m different branches was satisfied. And by carefully batching these things together, this OR proof itself can basically have a constant size, so independent of the size of each branch.
So it's an OR of all of the assert zeros for each branch?
Yes. So
you can't mix assert zeros from different branches? Exactly,
yeah. And the way we do that is actually just to kind of first compile the assert zeros from one branch down to a single assert zero in that branch. Then you have an OR of just m assert zeros.
Got it, thank you.
Okay, so just going over this quickly, I'm running low on time. So we show that this protocol can, this disjunctive protocol essentially applies to a broad class of protocols based on linear IOPs, which we formalized with a similar model. There's also some recent work which extends this to certain classes of Sigma protocols. And the communication cost we get is now proportional to the longest branch plus some additive overhead, which is linear in the number of branches. But we can actually do better. So once we have disjunctive statements, a nice thing to think about is actually nesting these disjunctions. So you have a program which doesn't just have a disjunction at the top level, it might have many different branches as you go deeper. And we can do this whilst avoiding some kind of exponential blow up in the depth of the disjunctions, and applying this with a kind of recursive procedure across combined with the basic protocol also allows to reduce this linear in M overhead to be logarithmic. This is something that can also be useful in other applications, like the Sigma protocol paper I mentioned also applies this to ring signatures. Okay, so very quickly, I'll just go over some rough performance numbers of some of these protocols. So here I've got the mac and cheese protocols, or some variants of them, as well as a Quicksilver protocol, which I haven't talked about, which is a recent concurrent work on ePrint, which uses a more efficient multiplication check for these information theoretic MACs or homomorphic commitments, which actually makes a non-black box use of the information theoretic MACs to do things better. But I won't go through this in detail, but the bottom line is that, okay, for arithmetic circuits, say you can get performances of around 1 million multiplications per second, where you're communicating just between 1 and 3 field elements per multiplication gate. If you use the mac and cheese protocols, you can additionally get these optimizations for disjunctions. And I've got also here this stacked garbling approach, which is zero knowledge from garbled circuits, which was previously the only kind of zero knowledge protocol in this setting, which was known to support disjunctions. But this is only for Boolean circuits and also has much higher communication because you have to communicate a single AES key essentially for every AND gate in the circuit. So with Vector-OLE, you get much lower communication and also computational costs compared with garbled circuits. Okay, and to wrap up, yeah, so I think the main takeaway is that Vector-OLE is a pretty recently developed tool from the multi-party computation literature that gives us this very nice homomorphic commitment scheme that turns out to be very powerful for simple types of commit and proof systems with low memory costs. And secondly, we can apply this stacking type optimization to get an all proof type construction with much smaller communication than normal for optimizing disjunctions. And I'll just briefly mention a couple of open questions. So I think there's a lot of interesting things to look at, but on the slide at the moment, I've just got a couple of kind of big, potentially challenging, but I think also interesting points. Firstly, getting smaller proofs. And of course, it'd be great to get something fully succinct. Perhaps one avenue to this is to try and build some kind of succinct vector commitments from Vector-OLE. Because right now, to commit to a single vector, then you have to build this, build this up one element at a time, which has linear communication. And of course, also important is trying to get something going beyond a single designated verifier. So even just extending it to multiple verifiers beyond naively running the proof between every single verifier, or ideally getting something that's fully publicly verifiable would be very nice in this setting.
So it's designated verifier because you're using max.
Exactly. Okay, and that's all I wanted to say. So thanks for listening.